R61, which is a novel multimodal neural-physiological and behavioral sensing and machine learning for mental states. So, of course, as we all know, brain and especially mental disorders are a leading cause of disability and unfortunately treatment resistant in many cases. And based on the evidence that these disorders are actually signs of abnormal activity across large-scale brain networks, one idea that we also focus on in my lab is whether we can come up with alternative therapies by trying to directly decode and regulate these abnormal activity patterns. But of course, to do this, we first have to have a way of modeling these activity patterns that we potentially record from multiple brain regions, and they're very complex, and then decode from them an underlying mental state, let's say mood in depression or anxiety, such that we can then use that decoding as feedback within a closed loop system to regulate these states. Now, this closed loop system could be a deep brain stimulation system. It could be a non-invasive neurostimulation system. It could be even pharmacological intervention. So the question is, how do we get that feedback signal in order to personalize our therapies within this closed loop framework? And of course, one element that we have to develop are these decoders that would decode mental states. And that's something that this particular R61 focuses on. Now, the way this is done, and you've heard a lot from others about this, for especially mental states, what we do is we record neural activity, and then our best behavioral surrogates are these self-reports. It could be iPad-based, it could be as complex as you want, but at the end of the day, they're these iPad-based kind of intermittent self-reports. And despite this, we've been able to make quite a bit of progress in developing kind of biomarkers and decoders. For example, in 2018, we showed that we can decode mood variations from intracranial human brain activity. There's been a lot of other beautiful work on biomarkers of different mental states across different disorders from many labs. And this is great, but in order to actually go towards translation of these ideas, we have to improve precision and robustness of our decoding. And that is the topic that we address, and we try to tackle it from multiple fronts. So first, on the behavioral front, as I mentioned, our best surrogates are these self-reports. But one issue with this is that they essentially omit social processes that we know are a fundamental and trans-diagnostic domain of emotional functioning and are affected across a diversity of neuropsychiatric disorders. The other issue with them is that they can have a very small dynamic range, which can be widened in naturalistic interactions. And finally, they're very sparse and have a very low temporal resolution of hours. So to solve this, we will develop conversational virtual human agents that can evoke naturalistic social processes. And further, we will obtain more continuous behavioral measures of mental states by incorporating audio-visual tracking based on subject videos. So that's on the behavior front. But the other question is, what about physiology? So of course, again, you've heard about this already. Physiological signals such as heart rate, skin conductance, and biochemical signals such as cortisol actually do relate to mental states. And because they're non-invasively measurable, they can be widely applicable. So can we augment our neural and behavioral measures with physiological measures? Again, there are multiple challenges. First of all, we don't have wearables that are multimodal and can actually measure all of these modalities, especially, for example, if you think about cortisol in combination with physiological modalities. We also don't know how these relate to neural biomarkers. So what we intend to do is to develop a first of its kind wearable skin-like multimodal sensor that can give us not only the physiological modalities like heart rate and skin conductance, but also cortisol that we can measure from sweat. So what is the third challenge? Let's say we have all of this data. Now we have to make sense of it. We have to analyze and build our decoders. But this is very challenging because if you think about all of these modalities that we are recording, neural, physiological, behavioral, if you think about brain states that give rise to them, there may be only a minority of these states that are actually related to the mental state that we are interested in. We call these behaviorally relevant states. So how can we actually disentangle these states from everything else going on that we have no interest in? So on that front, we are developing deep learning architectures that can dissociate these behaviorally relevant latent states. We call these multimodal RNNs. And we've already actually made some progress on this front by developing a deep learning approach called DPAD that can dissociate behaviorally relevant neural dynamics for behaviors such as movements. But what we have to do now is to extend these to these kind of mental state tracking behavioral modalities, also extend them to multimodal signals, including neural and physiological signals, to be able to assess these modalities and do decoding. In terms of experiments, what we are going to do to test all of these technical developments is to record intracranial activity in epilepsy patients across 7 to 10 days from cortical limbic regions. And within these patients, then record all of these modalities that I mentioned, audio-visual, self-reports, as well as wearable data. And finally, of course, there's a lot of ethical implication here. We are trying to infer the content of mental states, and this raises problems of mental privacy, and that can also undermine self-trust about subjective assessment. So we have actually a dedicated neuroethics team who are going to address this by developing quantitative interviews that assess the patient experience and their views of mental privacy and self-trust, such that that can be an integral part of our experimental and technical development. So here's what we're going to do. This is where we started, neural activity self-reports. We're going to have a virtual human that engages people in social interactions. We're going to have continuous audio-visual measurements. We're going to have wearable data. We're going to develop multimodal RNNs that can take the neural-physiological modalities and predict the behavioral measures of mental states, with the final vision that hopefully this would allow us to move closer toward multimodal and AI and sensing technologies that can extract mental states from human brain networks within social processes, naturalistic setups, and beyond, and eventually allow us to move toward these closed loop systems that can personalize a variety of therapies for mental disorders. So with that, I would like to thank my lab members, as well as the team within R61, which is across the Keck School of Medicine and the Viterbi School of Engineering at USC, and also neuroethics team is at UW. Thank you, and I'm happy to take any questions.